Good evening, my dear students. In this video, we are going to discuss about applications of Lagrangian formulation. Lagrangian formulation is a classical solution to derive the equation of motion of a particle by using generalized coordinate system. Now, we can also apply the same classical solution to many classical system. There are many classical system available. First we take a simple pendulum to verify the Lagrangian formulation by using the generalized coordinate system. We can simply define the simple pendulum. We can simply state what is a simple pendulum. It is a simplest primary classical system to verify all classical concept in easiest way. That is the advantage of simple pendulum. So we can take first system is simple pendulum. We can easily draw a simple pendulum, a string hanging by using a hook. So this is simple pendulum. Now we can apply a force. This pendulum is moving any one side of the pendulum like this. So this is O. O means origin, center point. We can take. And this is A. We put the name A. This OA is L. Sorry, this point is O, this point is A. The displaced position deflected, that means the deflected position is B. So OA is L and OB is also L because the length of the string does not change, but we can draw a line from B to OA. Then here we put theta. So whenever a pendulum moving from its original position or rest position or static equilibrium position, it moves from A to B, it makes an angle theta. Now we note this point is C. Now OC CA is L. So this is MG. This is also MG. So a mass attached with a string or a bob, it is hanging on a hook. This setup is called simple pendulum. Now some details we can write from the figure. So theta is the deflected angle. So deflected angle means it is lying between OA and OB, that is theta, and then L is the length of the pendulum. So this system is a two-dimensional system. So the simple pendulum is moving on the horizontal plane about its vertical axis. This is the actual position of the simple pendulum. Now we can write the kinetic energy of the pendulum, that is T equal to half mv square is the general form. We can easily write the arc AB is L theta. So here theta is varying with respect to t, therefore we can easily calculate or measure the velocity with respect to theta here. Then theta takes the form theta dot, because whenever the pendulum is oscillating, theta may change, L does not change, therefore theta is changing with respect to t, so it takes differential form. We can write this equation of m L theta dot the whole square, and also we can write of m L square theta dot square. This is the kinetic energy of the simple pendulum. Here m is mass of the bob or a string attached with a mass is called a bob, we can take. Okay, then dear students, two more points you have to remember mind here. First one is the pendulum is always directed towards the rest position. Rest position means it is a stable position. Okay, this is first point. And then the BC is decide the moving position of the pendulum, and the remaining portion is to rest. So whenever we go to calculate the potential energy of the pendulum, so this distance AC is involved with that, therefore the moving distance, that means action area is decided by point C. So this is the second point. Now we can write the potential energy. Potential energy V is equal to mgl. This is the actual potential energy, but here the action area is dominated at this point. The remaining length is dominated with potential energy. So we can write the L as L minus L cos theta, because the L is mentioned here OA minus OC. So already we mentioned here OA is L, and here OC is, we can make this triangle OCB. Here OB is L, this is theta, therefore we can derive cos theta is equal to OC divided by L. From this, L cos theta equal to OC, therefore we can substitute L cos theta for OC here, and L minus L cos theta, we get the potential energy from this equation. Therefore, finally we can write V equal to mg L minus L cos theta, and then V equal to mg L 1 minus cos theta is the potential energy of the pendulum. But we know that Lagrangian is T minus V, that is L equal to T minus V. We can put the solution from T and V of m L square theta dot square minus mg L 1 minus cos theta. But we know that the Lagrangian equation of motion is d by dt of dou L by dou qj dot minus dou L by dou qj is equal to 0. But we take here the generalized coordinate as theta, therefore qj is replaced by theta. Therefore we can rewrite this equation d by dt of dou L by dou theta dot minus dou L by dou theta is equal to 0. Then we have to derive the dou L by dou theta dot dou L by dou theta from this equation. So we can write the first value for dou L by dou theta dot equal to, and then dou L by dou theta. Here L taking with respect to theta dot. Here theta dot is existing in the first term only. So this term is 0. Then we can write the differentiation is theta dot square is take the form 2 theta dot. Therefore 2 is cancelled after we get m L square theta dot only. Therefore of m L square 2 theta dot, then we cancel 2 and finally m L square theta dot is the solution for dou L by dou theta dot, and then here L taking with respect to theta, so we take theta here only, so the theta dot will become as 0, and then dou L by dou theta is equal to 1 minus cos theta is sin theta. Therefore minus mg L sin theta is the solution for dou L by dou theta. Substitute these values in Lagrangian equation, then we can write d by dt of m L square theta dot, and here 1 minus and here also 1 minus, therefore we get plus mg L sin theta is equal to 0. Then we have to differentiate here. Alternately this term is also write like this, d theta dot divided by dt plus mg L sin theta is equal to 0. Then d theta dot by dt is also we can write as theta double dot. Therefore m L square theta double dot plus mg L sin theta is equal to 0. For our convenient, both terms are divided by ml square. Then here ml square is cancelled, therefore remaining is theta double dot plus here ml also cancelled and remaining is g by l sin theta is equal to 0. Here sin theta is the amplitude. It may be very small, therefore we can mention here sin theta as theta only. It is enough. Therefore theta double dot plus g by l theta is equal to 0. Then we get the solution from this equation for a simple harmonic motion. Simple harmonic motion, that is t equal to 2 pi root of L by G. Actually this is the final solution for the simple pendulum in Lagrangian form. Now suppose this oscillation is a simple harmonic motion, it will take the time period t equal to 2 pi root of L by G. That is the time period for angular simple harmonic motion. So that's all.